In this demonstration, we're going to show how the control strategies for the critical components of a bioreactor and the production of penicillin can be achieved. The first step in any process is to go and make sure that all the components used for the production are sterilized. This is typically achieved by running a steam in place process. For purposes of abbreviating this demonstration, we're going to assume that that has already been done in our facility. Our facility includes multiple reactors for the development of our product. It includes smaller reactors upstream, as well as separation and buffering tanks downstream of our main reactor. So the first step in our process after the steam in place process is to charge the reactor with the components needed to grow the culture. First step, we will charge it with the medium, which includes the micro and macro ingredients. So we'll charge 500 liters into our main bioreactor. We'll add antifoam, and we'll put 600 liters of that into our reactor. And as that's being added, we'll dose the pre-fermentation from our upstream reactor. We'll dump or dose 1,500 liters into our main bioreactor now. Those components are being dosed into the main reactor. We can begin our agitation of our solution. This is a variable speed drive that has the specific speeds already set for it. So we will go and start our agitator. Now that we've begun agitating, we can start our pressure control in our reactor. Our control strategies are looking for set points. At this point, we're setting a set point of 25 millibar for our pressure in our reactor. We'll start our control loop, where pressure transmitters will measure the temperature and pressure in the reactor and adjust the control valve to meet the set point of the desired reactor pressure. We'll begin airflow in our reactor. Again, our set point is being requested. We're going to set a set point of 21% dissolved oxygen in our reactor. How this is achieved is the control valves will measure the dissolved oxygen and adjust by putting more air and bubbling it through the solution as the agitator continues to stir our solution. Now that we've done that, we'll start our pH control loop. Our set point is going to be 6 for our pH. Again, pH sensors will monitor the pH of the solution and open and close appropriate acid and base control valves to adjust the pH to the desired set point. One final control loop will adjust the temperature control for this. Our desired set point is going to be 21 degrees C. We'll begin our control strategy. You can see in the lower right hand portion of our PNID drawing, we've got two heat exchangers, one for raising the temperature if the temperature of the solution is too low, and another for cooling the solution if the temperature gets too hot. So depending on what the temperature and the set point are, the heat exchangers will go and set the appropriate temperature for our solution. So at this point, we've charged the reactor, we've added all of the components to the reactor, and the control strategies are all running, and this is in the growing phase of our batch campaign. For the purposes of making this a faster demonstration, we're going to pretend that the full duration of the campaign has been achieved, and at this point we have the desired solution has grown the culture over the desired time as determined by the engineering groups involved. So now we'll go and transfer the solution from our main bioreactor to the downstream phase, which is a separation phase, where the product will be taken out of the solution and then later transferred to the finishing portion of our process. So we'll open up our transfer control strategy, and here we will discharge 2,500 liters out of our main bioreactor and we'll send that to the separation portion of our facility. As that is being transferred from our main bioreactor down to our separation facility, we can start stopping our control strategies. So we will cancel our pressure control strategy. We'll cease our airflow. We'll conclude our pH control strategy. We'll turn our temperature control loop off. And we'll turn our agitator motor off. And we will turn our pH control off. So at this time you can see that the solution has been transferred out of our bioreactor down to the separation phase. And now we can drain whatever waste products may be left still in the bottom of our reactor. At the conclusion of this process, we can again instantiate a steam in place process, and we'll sterilize the bioreactor and the components and prepare it for the next campaign for developing a pharma product. In this demonstration, I was controlling all the control strategies somewhat manually from a pre-programmed control algorithm for each of those parameters. In a more completely automated system, this would be run from a batch control center where the specific set points for each of the control strategies would be pre-engineered and set for the specific timing parameters as well as these set points for them. So just to show a steam in place process, at this point we'll set the steaming to have a set point of 120 degrees C. We'll start the steam in place process. And now we'll look at the temperature controller. So this is the faceplate for the PID drawing for the PID. You can see the set point is set at 120 degrees C. Process value is coming up. It's at 70 degrees. It's rapidly coming up. Eventually it will achieve the temperature desired. A more rapid response can be programmed in if that's desired by a more tightly tuned PID control loop. So again, the steam in place process may last for a number of minutes, or in our case it was set to be controlled for 25 or 27 minutes depending on which reactor we're trying to provide the steam in place process on. So this concludes our demo of the process of developing penicillin in a reactor, and a more complete control strategy would be used, or a modified control strategy would be used if we were not doing a batch campaign but we were doing a continuous culture growing period.